Three-dimensional computing, beyond binary logic introduction. Welcome to an exploration of three-dimensional computing, a revolutionary approach that extends beyond traditional binary systems. Today, we'll discover how this architecture leverages three states to achieve quantum-like capabilities while maintaining compatibility with classical computing. The limitations of binary computing. For decades, computers have operated on binary logic, the simple states of 0 and 1. While powerful, this approach has inherent limitations. Binary systems have limited information density, can only represent two states, and face computational inefficiencies for certain types of problems. These limitations have led us to explore alternatives that expand the computational landscape. Introducing three-dimensional computing. Three-dimensional computing introduces a revolutionary third state. While traditional binary computing uses only 0 and 1, our approach adds a third state, -1. This creates a trinary system with values -1, 0, and 1, opening new possibilities for computational efficiency. This trinary approach offers several key benefits. More information per digit, with log2-3 or approximately 1.58 bits of information per trit, compared to 1 bit in binary systems. It enables logical operations with three distinct states, providing more expressive computing capabilities. Certain algorithms become significantly more efficient in this three-state system. And perhaps most importantly, through a technique called signal flattening, we maintain full compatibility with existing binary systems. Trinary logic operations. Let's examine the fundamental logical operations in trinary computing. The AND operation in trinary logic follows this truth table, where we now have three possible inputs and outputs. Notice how -1 interacts differently with other values compared to traditional binary logic. Similarly, the OR operation has been extended to accommodate the third state. When either input is 1, the output is 1, but when inputs include -1, we get different behavior than in binary systems. The NOT operation in trinary logic is also different. NOT -1 equals 1, NOT 0 remains 0, and NOT 1 equals -1. To illustrate how these operations work, let's compute a simple example. -1 and 1. Following our truth table, we see that this equals -1. This demonstrates how the third state provides new computational possibilities not available in binary systems. Signal flattening. One of the most powerful aspects of three-dimensional computing is signal flattening, a mechanism that enables seamless binary compatibility with zero computational overhead. Signal flattening is remarkably simple, yet powerful. It treats -1 as functionally equivalent to 1 in binary contexts. When we need to interact with traditional binary systems, -1 and 1 are both interpreted as true or 1, while 0 remains false or 0. This approach offers several key advantages. Both -1 and 1 are treated as true in binary contexts, enabling seamless compatibility. The flattening occurs at the hardware level with zero computational overhead. It allows existing binary software to run without modifications, and it can be selectively disabled when full trinary capabilities are needed. The Trifactory Engine. At the heart of three-dimensional computing is the Trifactory Engine, a software layer that manages the translation between trinary and binary computing paradigms. The Trifactory Engine consists of several key components. The Signal Flattening Unit handles compatibility with binary systems. The State Management Unit tracks the three-state values throughout computation. The translation layer converts between binary and trinary representations. The optimization analyzer determines the most efficient processing mode, and the execution scheduler coordinates operations across the system. The engine provides several key functionalities. Dynamic state management intelligently switches between processing modes. Resource optimization maximizes computational efficiency. Conventional quantum translation enables quantum-inspired algorithms on classical hardware. Signal flattening ensures binary compatibility, and the binary compatibility layer runs existing software without modification. Hardware implementation. Three-dimensional computing can be implemented in hardware through several approaches. In voltage-based implementations, we use three distinct voltage levels, -1 volt, 0 volts, and +1 volt to represent our three states. The trinary memory cell, TMC, extends traditional memory designs to store three distinct states. This increases information density while maintaining reliability. An alternative approach uses spintronic implementation, leveraging electron spin states, up, neutral, and down. This may offer advantages in energy efficiency for certain applications.